We all know that if you consider any strong acids which can easily undergo ionization and give rise to the respective cations and anion. The dissociation consider weak acid where the weak base can be related to the ionic product of water and it is equal to 10 to the power of minus 14 at 298 Kelvin. When these elements form a bond with an hydrogen, their sizes will be also increases as we move down the group. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with a unit called equilibrium. Under this unit, we have discussed about the Lewis theory of acids and bases, that is the last theory on acids and bases. In addition to that, we also solved the sum of the numericals based upon the equilibrium constant. Today, let us move on to the next topic of this unit by understanding ionization of acids and bases. And also we are going to discuss with the dissociation constant for the weak acids or for the ionization constant Ka, and we are also going to derive the dissociation constant or the ionization constant for weak bases, okay, that is Kb, and polybasic acids and polyacidic acids we are going to understand, and the factors which are affecting to the acid strength we are going to understand, and finally we are going to deal with the new terminology, that is pH of the solution and pOH of the solution. Let us start with the ionization of acids and bases. We all know that if you consider any strong acids which can easily undergo ionization and give rise to the respective cations and anion. For that, we need to understand the ionic product of water. We know that water is a weak electrolyte, correct? No? Water is a weak electrolyte and it undergo partial ionization. Why it is a weak electrolyte? It is not completely undergo ionization process, but it can undergo only the partial ionization. Hence, it is an example for weak electrolyte. You can see that the water which is upon ionization to give a H plus ion and OH minus ion. For this equation, now I'll apply the law of mass action. What does the law of mass action says? It is nothing but a ratio of the product molar concentration divided by molar concentration of the reactant. So now I'll apply the law of mass action to the above equation. So I can write that K is equal to molar concentration of the product divided by molar concentration of the reactant. So these two are my product and this is only my reactant. Okay. Now I multiply the K with molar concentration of the outside. So K into molar concentration of the water, which is equal to molar concentration of the H plus into OH minus ion. Now I'll call the K into molar concentration of water as Kw. Okay, it is nothing but a ionic product of water. What is a Kw? Kw is a ionic product of water. Okay. So Kw is equal to molar concentration of the product, that is H plus into the molar concentration of the OH minus ion. Then how I can define the ionic product of water? So I can define it in this way, that is the ionic product of water is a product of molar concentration of the hydrogen ion and the molar concentration of the hydroxyl ion in water or in any aqueous solution. So what is a Kw? Kw is nothing but a ionic product of water and it is nothing but a product of molar concentration of the hydrogen ion into the molar concentration of the hydroxyl ion in the water. So this is known as what? ionic product of water. So where you can see that the water is even though it is a weak electrolyte, undergo partial ionization and give rise to the ionic product of water. Now we need to find out at constant temperature, that is at 298 Kelvin, what is the value of Kw? Kw, it is nothing but a ionic product of water. At 298 Kelvin, the ionic product of water will be always equal to 10 to the power of minus 10. So now I can rewrite this above equation as 10 to the power of minus 14, which is equal to molar concentration of the hydrogen into molar concentration of the hydroxyl ion. Okay, because at 298 Kelvin, Kw will be equal to how much? 10 to the power of minus 14. Okay, this is the equation we got. Suppose if the solution is acidic, what will be the values of Kw? We'll see now. So if the solution is acidic, the molar concentration of the H plus ion will be greater than the molar concentration of the OH minus ion. If the solution is basic, the molar concentration of the H plus ion will be lesser than the molar concentration of the OH minus ion. If the solution is neutral, then molar concentration of the H plus ion will be equal to the molar concentration of the OH minus ion, and it is nothing but a ionic product of water, and it is equal to 10 to the power of minus 14. Okay, or to the 10 to the power of 7 you can write in terms of NEET. Okay, so this is how we can understand the relationship between the acidic as well as the basic solution as well as with a neutral solution. Next we have the dissociation constant of weak acids or ionization constant Ka. So what is a Ka here? Ka is nothing but a dissociation constant of weak acids or ionization of weak acids. Let us consider the weak acid Ha, which ionizes partially with water and gives to the H3O plus ion and A minus ion. So which is my electrolyte? My electrolyte is a weak acid, that is Ha, which is allowed to react with what? Water. So what will happen? We know that weak electrolyte undergo partial ionization, correct now? So thereby the water which is going to accept one of the proton and become H3O plus ion, and remaining A minus ion will be comes out. Okay. Now for this reaction, I'll apply the law of mass action. So what does the law of mass action tell us? So K, which is equal to the molar concentration of the product divided by molar concentration of the reactant. Here my products are nothing but a H3O plus ion, whereas my reactants are HA and H2O. So I can write H3O plus ion into A minus ion divided by molar concentration of HA into molar concentration of water. Okay, this is what we get when we apply the law of mass action. Now I'll take out this molar concentration of the water outside. The K into molar concentration of the water, when it comes outside, the remaining is molar concentration of hydronium ion into molar concentration of the A minus divided by molar concentration of the weak acid, that is HA. We know that the K into molar concentration of the water, which is nothing but a dissociation constant, that is Ka. Okay. So I'll write K into H2O, which is nothing but a Ka. K is nothing but a dissociation constant. So Ka is equal to molar concentration of the hydronium ion into molar concentration of A minus divided by molar concentration of the Ha. So how can I define the Ka now? So Ka is nothing but a, what is the Ka value we got? Ka is nothing but a molar concentration of hydronium ion into molar concentration of the A minus divided by molar concentration of the weak acid. Correct, no? So, how can I define this Ka now? So, it can be defined as ratio of product of molar concentration of dissociation of the ions to the molar concentration of undissociated acid molecules at given temperature. So, what does it is? It is nothing but a ratio of molar concentration of dissociated molecules divided by molar concentration of the undissociated acid molecule. So, this is known as what? Dissociation constant of weak acids. Okay. This shows that the larger the values of Ka, stronger will be the acids, and smaller the values of Ka, weaker will be the acids. If the Ka values are high, then the acids are strong. Okay. If Ka values are very low, then the acid is weak. Then it is a weak acid. This is how we can understand the dissociation constant of the weak acid. So, hope you are understood with this derivation. We have one more derivation for dissociation constant of weak base, and it is represented as Kb. Let us consider the weak base, that is BOH, which is my weak base, okay, BOH, which is allowed to react with the water molecule. We know that our water molecule, which takes up a proton, thereby it forms OH minus ion plus B plus molecule. Okay. So, this indicates that our weak base is undergo partial ionization. Now, for this equation, I will apply the law of mass action. So, what will happen if I apply the law of mass action to the above equation? So, K is equal to molar concentration of the product, that is molar concentration of the hydroxyl ion into B plus divided by molar concentration of the BOH into water. Now, what I will do? I will take out the molar concentration of the water outside, and remaining is molar concentration of the hydroxyl ion into molar concentration of the B plus divided by BOH. Okay. Now, I call the equilibrium constant K into molar concentration of the water, which is equal to Kb, which is nothing but a dissociation constant of weak base. Okay. So, Kb is equal to B into OH minus ion divided by BOH. Now, how can I define this dissociation constant of weak base? What is the equation we got? Kb is equal to molar concentration of the hydroxyl ion into molar concentration of the B plus ion divided by BOH, molar concentration of the BOH. How can I define this? It is nothing but a ratio of molar concentration of dissociated ion divided by molar concentration of the undissociated base molecule. Okay. This is how I can understand the dissociation constant or the ionization constant of weak base. So, now hope you all understood the derivation for dissociation constant of a weak acid as well as the dissociation constant of weak base. Now, let us see what is the relationship between the dissociation constant of weak acid with the dissociation constant of weak base. That is, the dissociation constant of weak acid into dissociation constant of weak base will be always equal to the ionic product of water, which is nothing but what? Ionic product of water. And we understood that ionic product of water, which is equal to 10 to the power of minus 14. Now, I can write the dissociation constant of weak acid into dissociation constant of weak base, which is equal to 10 to the power of minus 14 at 298 Kelvin. This is how the dissociation constant of weak acid with the weak base can be related to the ionic product of water, and it is equal to 10 to the power of minus 14 at 298 Kelvin. the polybasic acids and polyacidic bases. What is this? A polybasic acids are acids which can donate more than one H plus ion. So the name itself shows that it is a polybasic acids. So which are having a capacity to donate more than one H plus ion. Such acids are said to be a polybasic acid. What about polyacidic bases? These are the bases which can donate more than one hydroxyl ion. Which can donate what? More than one hydroxyl ion, and such bases are called as polyacidic bases. We have an example for this, that is phosphoric acid or orthophosphoric acid. You can see that in this examples, it can donate the 3 OH ions. Correct now? It can donate how many OH ions? The 3 OH ion. Hence the molecular formula will be H3PO4. Or you can say that it can replace only 3 hydrogen atom. In the H3PO3, that is in orthophosphorus acid, you can see that there are 2 hydroxyl groups are free to replace. Correct now? Whereas in case of hypophosphorus acid, even though we have the 2 hydrogen atom, okay, only 1 hydrogen atom will be available for the replacement, whereas the another hydrogen is not available for the replacement because it is directly bound to the phosphorus. Here also you can see that it is directly bonded. This is about the polybasic acids and polyacidic bases. In polybasic acids, the dissociation constant value, that is dissociation constant of a weak acids value, that is Ka1, Ka2 and Ka3 are nothing but a first ionization constant or first dissociation constant and the second dissociation constant and the third dissociation constant respectively. But the Ka1 will be greater than Ka2. Similarly, the Ka2 is greater than Ka1. This indicates that it is more difficult to remove a proton from the negative ion due to the electrostatic forces. Due to what? Electrostatic forces. So it's not very easy to remove the H plus ions from the negatively charged ion. So that is why in this orthophosphoric acid, as I said, we can easily remove the 3 hydrogen atom, whereas here even though the 3 hydrogen atoms are available, only 2 hydrogen atom we can replace it because one is directly bonded with the phosphorus. Here only 1 hydrogen atoms are available and other 2s are directly related to the central metal atom. So this is how the ionization constant, that is K1, K2, K3, which is very much larger as it is from the first one. So to remove the first proton, it is very difficult. For removing the second proton, we can say that. So it's not very much higher than that of the first one. For removing the third proton, it is very easier than the second one. This is how we can understand the polyacidic bases and polybasic acids. Next, we have the factors which are affecting to the acid strength. We have only the 2 factors. One is bond strength, other one is polarity. Let us understand how does this bond length as well as with the polarity which affects to the acid strength. As the size of the element increases down the group, the bond strength will be decreases so that the acid strength will be increases. As we move down the group, that is with fluorine, chlorine, bromine and iodine, okay, what will happen if it is form a bond with an hydrogen, okay, bromine and iodine, as it is moving down the group, when these elements are form a bond with an hydrogen, their sizes will be also increases as we move down the group. As the size increases, imagine this is a fluorine and this is our hydrogen. So as we move down the group, what will happen? the size which is also going to be increased. Correct, no? So, the bond length will be also get increases. Correct, no? So, as the size increases, the bond length which is also get increases. So, it's very easy to break this bond as it is compared with the smaller atoms. So, this indicates that the bond strength will be go on increases as we move down the group. That is mainly because as we move down the group, the size of the atom increases and the bond length will be increases. If the length of the bond which is increases means it is easier to break as it is compared with the two closed one molecule or two closed one atoms. Next we have polarity. As the electronegativity increases in the same row, the polarity of the substance increases. Therefore, the acid strength which is also get increases. So, what will happen as we move across the row? Okay. So, we have seen that the electronegativity is also get increases. Correct, no? As a result of this, acidic strength of an acid which also get increases, and it will be in the order of methane, ammonia, then with water, then with hydrogen fluoride. Next we have the pOH of the solution. So already in your 10th standard you have studied that what is the pH of the solution, correct, no? So in your previous class only you have studied about the pH of the solution. So it can be defined as the negative logarithm of base 10 of molar concentration of the H plus ion in the solution, and it is proposed by Sorensen. So what does it mean? It is nothing but a negative logarithm of base 10 to the molar concentration of the H plus ion, and it is nothing but a pH. And this definition was given by Sorensen. Now, if you remove the negative log from this above equation, I can rewrite this pH as log base 10 into 1 divided by molar concentration of the H plus ion. Now, already you have an idea about the pH scale. It will be ranges from 0 to 14. It will be ranges from 0 to 14. And at the center, we call that, at the point 7, we call this place as a neutral one, neutral state. Okay. Now, from 0 to 7, we call it as acidic solution. Above 7 to 14, we call this basic solution. Again here, 2, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, and this is a 14. Okay. So, at the neutral point, that is at 7, we say that solution is neutral. From 0 to 7, we call it as acidic solution. After 7 and above, we call the solution as basic solution. So, this is known as what? pH scale. So, the pH scale will be having the ranges from 0 to 14. At the point 7, we call that place as a neutral place where the solution does not show acidity or basicity. Okay. But below the 7, we call such solutions as acidic solution. Above 7, we call such solution as basic solution. Now, if you think about the pH, we need to know about the pH of our blood. So, the pH of our blood will be 7.35. So, it comes under here. So, it is 7.35 and it is slightly basic in nature. This is how we can understand the pH scale, and it was first given by Sorensen. Next, we have the pOH of the solution. It can be defined as, it is a negative logarithm of base 10 to the molar concentration of the hydroxyl ion in a solution. So, what is the pOH? pOH is nothing but a negative logarithm of base 10 into the molar concentration of the hydroxyl ion. Now if you remove the negative log, so you can rewrite this above equation as log 10 divided by 1 divided by molar concentration of the hydroxyl ion. At 298 Kelvin, you can say that the pH of the solution plus pOH of the solution, which is equal to 14. Okay. So, in the neutral compounds or in the neutral solution, you can say that the pH, which is equal to the pOH, and it is equal to 7 only at the neutral solution. But in general, when you are talking at 298 Kelvin, okay, pH and pOH will be always equal to 14, which is nothing but a pH scale number. So, in the next class, we are also going to understand the derivation for pH plus pOH is equal to 14. So, hope you all understood this session. I will come back with the next session. Till that, take care and be safe. Thank you.